Hey guys, so in this video series, we are going to be going through Griffiths Quantum Mechanics Chapter 1, and in future videos, through all of the chapters in Griffiths' book. And so to start off, we're going to start with Chapter 1, the Schrodinger equation. The Schrodinger equation is the main equation in quantum mechanics. So Griffiths explains, in classical mechanics, we deal with, Newton's law of motion. The sum of the forces is equal to the mass times the acceleration of a particle. Or we have to use energy to solve what the velocity is, or figure out what the position as a function of time is going to be. In quantum mechanics, we take a different approach. As we'll find out, it's a statistical approach. We use what's called in quantum, we use the wave function, psi of x and t. And so where our first input variable is the position that we're interested in, and then the second input variable is the time. And we'll be starting off with the one-dimensional Schrodinger equation, which tells us how to solve for our wave function. And what the wave function is, it's essentially all the information we can obtain, which is extremely useful. I mean, if this is all the information we can obtain from the system, that would be a very useful object to study. And so we can look at the Schrodinger equation and just see, so this is a partial differential equation, second order, and let's look at some of the input variables. So we have h bar. So h bar is a constant. It's a constant that equals to Planck's constant divided by 2 pi, which is approximately equal to 1.054 times 10 to the minus 34 joule seconds. So we can see that this right here is the units. It's in joule seconds. Okay. And so the next thing we see is that we take the partial derivative of psi with respect to t. So I, the imaginary number, h bar partial derivative of psi with respect to t is equal to, if you've taken classical mechanics and some of the advanced portions of classical mechanics, you'll see that, this is the Hamiltonian. So minus h bar squared divided by 2m times the second partial derivative of psi with respect to x, plus the potential energy function times psi. And we have to solve this partial differential equation to figure out psi. And we can see where the environment comes in at. So it's very telling that, so these are constants, constant, this right here is what we're going to be using to solve. So it's kind of not necessary, but our environment comes in through right here. Our environment comes in through the potential that's multiplying psi, and our particular object in that environment comes in through the mass. You can see that there's really only two ways that we can adjust this function, because everything else is staying the same. And so depending on variations of the potential and variations in the mass are going to give us different wave functions, which seems kind of crazy, right? Because, say we have the exact same environment and we have two objects of, the same mass, it's going to be almost impossible to tell them apart. And so quantum mechanics gets at really deep fundamental questions of reality, which are addressed later on in the book, such as, how do I discern things from one another? And so as we go forward, we're going to figure out how we do this, and hopefully we get to learn a lot. So this right here was just a kind of a introduction into classical mechanics, into quantum mechanics, and as we go on through the book, our understanding will grow over time. So thank you for watching.